Okay, so welcome back, everyone. So the topic of today's lecture will bring us finally towards actually looking for fundamental physics, looking for physics beyond the standard model, using gravitational wave signals. And today we'll be talking about using what I call transient gravitational wave signals. So this is the type of events that have been seen in LIGO, something like black hole mergers or neutron star mergers. And then tomorrow we'll turn to a different type of signals, which is stochastic gravitational wave backgrounds. So let me start with just giving you, okay, so first, so when I mean BSM, BSM here can be a lot of things, right? So BSM could be something like some types of dark matter, right? So it could be physics beyond the standard model of particle physics, but it could also mean BSM in the sense of physics beyond the standard model of cosmology or extensions of GR, right? So I'm using BSM very loosely, and we'll see what type of physics we can potentially look for with these types of events. Now, I want to start by basically just giving you a result, which I was initially planning to derive yesterday, but I didn't get to it. So the derivation is in the notes. So I'm just basically just going to more or less give you the result because we need it. And because I got very scared of what happens when you go over time here, right? So, so if there is time at the end, which I doubt very much, you can always go back to this. But so, because we talked a lot about propagation of gravitational waves, but we didn't really talk about what is the condition to source a gravitational wave. Right, so imagine you have some source, right, and some center of mass, some coordinate y inside the source, some observer at some distance x from the source, right, where the statement is that this x is much, much bigger than the size of the source, right? So we're very, very far away from the source. And then what we can do is that we can do the exact same thing as we do in electromagnetism in the far field limit. Right? We have our equation of motion, box h bar mu nu is minus 16 p gt mu nu. We can solve this in the Green's function for the box operator. So then we get h mu nu, solve, basically formally solve 4g over r integral over the source. And then inside, we have the retarded source term. Right? So we make an observation at time t at some distance r. And what matters is the source at the time when the gravitational wave was emitted in the source. This is the exact same thing as electromagnetism. Now, what you do is you need to evaluate this integral. Right, so you need to figure out what exactly is this object. And that's a step that I'm going to skip. And I'm just going to tell you the result. And the result is that in TT frame, which we can use over here, far away from the source, the gravitational wave is given by 2g over r, the distance to the source. Then we have a projection operator. And then we have the second derivative of the quadrupole moment evaluated at the retarded time. So this projector here is the TT projector. So it just makes sure that kind of whatever you did on the left-hand side to get this into TT gauge, you have to do the same on the right-hand side.
Is there a KL on the I? Indices?
Yes, yes, yes. And so this guy is the quadrupole moment. So it's d3y, yk, yl, and then we make it traceless, multiplying t0, 0. Okay, so that's the usual way of computing the quadrupole moment in any mechanical body. And what this tells you is that in order to source the gravitational wave, what you need is a quadrupole moment, right, meaning something anisotropic. And what you need is an accelerated quadrupole moment, right? So it needs to have a time dependence. And then the amplitude of the gravitational wave scales as 1 over the distance. Yeah.
It's a quadruple moment just because we are choosing TT gauge, or is independent of the choice?
I mean, the physics is independent of the choice, right? I mean, this is just kind of how we express it. I mean, this is kind of a property of the source, right? This is the frame that we use to describe this far away, right? So the physical statement is independent of the frame.
So when you say we're in TT gauge, it's like in a TT gauge, far away, or
Yeah, it's an approximation, and this. I mean, we're choosing exact TT gauge, but the results are approximate to corrections of this order, right? To corrections of y over r, size of the source over distance to the source. The other approximation here is that we're assuming, probably assuming again that this. Well, I don't know if we're assuming it here, but in other parts of the lectures we've assumed non-relativistic, right? So we typically run into trouble if the source is moving at the speed of light. Yeah, and I mean, the duration is not very long normally, right? Depends on how many questions you ask. But you have it in the notes. But it's technical, right? There's nothing exciting really going into it. Okay, so why did I put this here? Is because we need it, and we need it when we talk about binary systems. So what is a binary system? Think you have two black holes in some coordinate system on the xy plane, right? And they are going around with some mass m1, m2, some position x1, x2. And that's the system we want to describe to see what sort of gravitational waves you get. In some sense, that's a pretty minimal system, because one black hole by itself, right, will never give you gravitational waves, because everything that is perfectly spherically symmetric will not have a quadrupole moment. Here, since you have the two black holes, it will give you a quadrupole moment. So this type of a system, and it's moving, right? So this type of a system will give you gravitational waves. So this system you've probably solved in your classical mechanics class, right? Which I'm sure you remember. So what you do in order to solve the system is you go to reduced coordinates, right? You introduce the reduced mass and write it as an effective one-body system. So you have the set of may or may not have some motion that we don't care about, and then we have the effective one-body problem with a particle orbiting around the center of mass. So the reduced mass is mu, m1, m2 divided by m1 plus m2. We will also need the distance between the two black holes, right? So let me call that, in this notation, x2 minus x1. We will need the total mass, m1 plus m2. And we will also need what we call the chirp mass, which is another linear combination of these masses, which is mu cubed capital M squared to the power 1/5. Now, Kepler's law tells you the frequency at which these orbit around each other, where I'm assuming here, just for simplicity, that everything is perfectly spherical. There's no ellipsis. Well, already because I can't pronounce it, it's not there, right? So perfectly circular, omega squared. So this is the omega here of the, well, let me call it the omega of the source, omega s, gm over r cubed. And now we just very explicitly, so now we fully described kind of the mechanics of the system. So now you can just take these results, right, and plug it into that expression here, right? So you will get something that these coordinates x1, x2, or the effective coordinate r, that's what we, well, the coordinate of the effective particle rotating here that will just be kind of, well, describing a circle, right? So r cosine omega t, y sine omega t. So you can plug that very explicitly into this expression. You can compute the quadrupole moment, and from there you can compute the resulting gravitational waves. So it's a homework exercise. It's just a couple of lines. I encourage you to do it just to really have the satisfaction of computing by yourself what LIGO actually sees. So what we want to compute is the gravitational wave at a distance from the source, where we're going to make our lives easier and assume that the observer is located here on the z-axis, right? Otherwise, you have a projection factor from the angles. But let's make our life simple. So then we take the expression up there, 2g d is what I called it. And now this projection operator basically tells you that you're going to get the same structure here on the right that you have on the left, right? So if I'm looking here for the plus polarization, what I'm going to have over here is I dot, I call it, yes, minus I double dot yy divided by 2. Okay, so this expression here is the doing of this projection operator that is telling you that the plus component is the one that has the diagonal elements with the different sign, whereas the cross component is the one that has the off-diagonal components. So now you plug everything in here, and you get minus 4 over d g mc to the power 5 over 3 omega source to the power 2 over 3 cosine 2 omega source t. Okay, so why do you get a factor 2 here? You get a factor 2 because you have some product of cosine and sine, right? So then when you multiply them and you use your theorems, you get a factor 2. So this tells you that the gravitational wave is oscillating at twice the frequency as the system of black holes which is rotating. And we also see again, of course, that the amplitude goes as 1 over the distance, so the further you are away, the more difficult it is to detect. And we note, that will be important in a moment, that the amplitude grows as a function of the frequency. Now, later, we will be interested in objects that are really at cosmological distances. So for cosmological distances, the thing that changes, that this guy, the distance, becomes the luminosity distance, right? So you get a factor of the scale. So this becomes the luminosity distance, which is 1 plus z times this guy here. And the other thing that, of course, happens is that the frequency redshifts. So far, we have implicitly assumed that there's energy conservation here, and that it's a completely static system, right? Because if normally in Newton's mechanics, if you have two objects on an orbit like that, that's completely stationary, right? They stay in this orbit forever. Now, we've just computed that they emit gravitational waves, so energy conservation tells you they're not going to stay on this orbit forever, right? We're going to lose kinetic energy of the orbit, which means the orbit is going to shrink. So does that make our computation inconsistent? It does not, because the rate of energy loss, I mean, gravitational waves don't carry away a huge amount of energy, in particular kind of when the black holes are so far away. So the rate of energy loss is much, 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 much slower than the oscillation frequency of the black holes, right? That is what we have implicitly assumed, and which is fine until we get too close, right? Then this will break down. So what we can do is we can say, okay, we've made this calculation. Right now, we can simply compute the energy emitted in form of these gravitational waves, and we can kind of plug that back into our equations for Kepler's law and basically have an orbit or in frequency which becomes time dependent. So if we do that, so if we account for energy loss due to gravitational wave emission, what you find is that now the frequency of the gravitational wave, right? So compared to the source, right? So this would be too small. So this, right, will be omega gravitational wave with the factor 2. And then there's a 2 pi to go from omega to f. But obviously, when you build a detector and you measure some frequency, you typically measure in linear frequency, not in angular frequency. So what you get is that there's some prefactor, 96/5 pi to the 8/3. There's again this factor g chirp mass to the 5/3. And then there's the frequency to a positive power, 11/3. So again, the logic of how you derive this I just explained, right? The details are, for example, in Majora's textbook. Now, what this tells you is that over time, the black holes will move closer together, and the frequency will increase. If the frequency increases, according to this expression, that's this expression, the amplitude will increase. Okay, so the type of signal that we expect is something that is initially oscillating like a cosine, and then as time evolves, it starts to oscillate faster and with growing amplitude. Right, so this is always, I failed drawing this. Okay, and then boom, right, the black holes collide. So that's the type of signal that we expect from these mergers. This is the type of signal that LIGO has seen. And this is what people call the chirp signal, right? Because like a bird, it goes up in amplitude and frequency towards the end. Okay, so what do we learn from this? This type of signal at leading order, what is to say we detect a signal, LIGO has detected signals like this, right? So at leading order, what can we observe, right? So we can observe at leading order, so observables, something like the amplitude, the frequency, and let's say the derivative of the frequency, right? Then, of course, if I can see the signal for long enough, right, I can maybe even kind of get more information, but that's roughly maybe what I would want to see. Now, how many parameters do I have in the problem? All right, so the parameters that I have in the problem, I have, so I have the two masses, right? So which I can say that the parameter that I will care about is the chirp mass, and then the other mass parameter I can write as the mass ratio, right? Equivalently, I could have also said I have the M1 and M2 as two independent parameters, but since the chirp mass is the thing that appears directly in the expressions, that's the one that is easy to constrain. This is the one that is hard to constrain. We have the luminosity distance. We have the actual distance, right? Or in other words, there's a question of redshift between the two. And you can see that from the expressions that we have here at leading order, it's completely degenerate, right? We can only measure the luminosity distance at leading order. And same at leading order, right? So we can only measure this guy, and we can only measure this guy. A priori, we don't have access to this, we don't have access to this. And then there's also other things that you would want to know. You would, for example, want to know maybe the inclination angle to the observer, right? Something that we have to set to 0 in this simple calculation. That will give you a projection factor, which will change your amplitude. So again, it is degenerate with the measurement of the amplitude. You will also maybe want to know if these objects had any spins. At these black holes that you were observing, you may want to know if they are actually black holes, or if they were maybe neutron stars or something else, meaning you would want to know as they get close together do they really stay perfectly spherical, or do they start to get deformed? Right, so we'd want to maybe know what is called the deformabilities, lambda 1, lambda 2, which become important when the black holes get very close. So they become important when you kind of get very much into this merger phase, which is the phase where all our approximations break down because the things are close together, they go close to speed of light, and it becomes, when the strong field limit of gravity, and it becomes very complicated. And then you may want to know if there's maybe some BSM physics hiding there, right? And that you want to disentangle from all these other parameters that are in the merger. And this BSM physics can come with however many parameters you may want to put in. So, okay, now you may see, okay, this is hopeless, right? But it's not hopeless. The reason it's not hopeless is that these are only the leading order observables that you have. And you can do better because, as I said, in this entire thing, we've just done the Newtonian approximation. So we're kind of maybe able to well describe things up until, say, here, right? Qualitatively, we understand kind of what happens at the end, right? I mean, it just increases to go up in frequency and amplitude until the black holes literally touch, then they merge. And after they merge, there will be some sort of ring down phase where the excited black hole kind of oscillates a bit before it kind of becomes a ground state black hole. And so there is more information in this phase than in this phase, right? There's kind of corrections to the Newtonian approximation, which depend on these other parameters. And so if you're able to very accurately predict what's happening here, you can, as a function of the parameters, you can extract more parameters. And that's what is used to break the degeneracy for these objects. So this is why, for example, when LIGO makes a measurement, they typically have a good measurement of the chirp mass, but it's not fully degenerate in M1 over M2, right? You will get some sort of ellipsis, which is much more constrained in this direction, but they do also have some constraint on that direction. And then here in this ring down regime, there's other types of perturbation theory. You can use black hole perturbation theory, which again gives you access to some of the parameters of that new system, and again helps you to give you access to some of these things. So we actually, remarkably, have access from the measurements that LIGO has done. They have put constraints on all of these parameters, right? So depending on how well they see the merger, how close it is, some of these kind of posteriors are very large, right? And you may say, well, you didn't learn that much, right? But then you make a lot of measurements, you gain statistics, and you do start to understand. So we actually, from doing the full analysis and not just the Newtonian approximation, we can access all of these parameters. Right, so the question is, how do they gain information on the spins? So you see that in a Newtonian approximation, they don't enter at all, right? So you have to go to the post-Newtonian or post-Minkowski expansion. So you have to go into the details of this merger phase, which is a whole another 5 sets of lectures or something. And I'm not expert. But a lot of theoretical effort goes into accurately determining these waveforms. And this is why it matters, right? Because you really need, because you'd think, I mean, sometimes for some of the events, we have, even hundreds of oscillations before we get into the phase where the approximation breaks down, and then we have a few where it breaks down. So you'd say, well, whatever, maybe I can just drop my past few oscillations and I can still do the physics. But there's kind of physics which, by construction, you can only access in this regime, right? So that's why it's so important to actually nail down and have a fast way of, because we can compute this in numerical relativity, right? I mean, we know GR. But the problem is numerical relativity is expensive, and these are many parameters, and you can't run simulations where you're scanning over all of these. Too expensive. So this is why people are working on analytical or semi-analytical ways to kind of nail down what happens in this region as a function of the parameters. Yes?
How can we test deviation from GR if we need the secret from GR to
to detect the gravitational wave.
Good. So the question was, how can we test deviations to GR? And we'll get to that in 15 minutes. I mean, if it were a very big deviation from GR, right, you would already, I mean, here we have a prediction, right, of what, at least for the in spiral, what it should look like, right, just computed using GR, right? So if we saw something that looked completely different, that would help. Okay, any other questions? No, you wait until I put the board up, right? And then you tell me some index is wrong. Okay, so let's talk about ground-based detectors, right? So LIGO, Virgo, Kagra, existing ground-based detectors. So I'm going to very briefly sketch how they work. I'm sure some of you know. And then I want to just tell you some science highlights from my very personal selection of stuff that we've learned about fundamental physics by the observations that we've made so far, and what is the prospect of learning more. And then later, if we have time, we'll talk about LISA, which is space interferometer, and then tomorrow we'll talk about pulsar timing rays. Okay, so let's say you have an interferometer, right? So you have a beam splitter, you have a mirror here, you have a mirror there, 1, 2, 3. You have a gravitational wave coming in. We're going to be working in TT gauge. And let's say we want to study what's going on along one arm of the detector, which has length L and unit vector L hat. So what we actually want to compute is the change, the difference. So we have a photon emitted in this direction, bounces off the mirror, comes back. A photon emitted in this direction, bounces off the mirror, come back. And here we interfere. So what we want to know is the difference in proper time that this trajectory takes as opposed to what this trajectory takes. And that difference in proper time will relate to a phase shift in the phase of the photon when they arrive here, or the phase of the laser when it comes back. And that phase shift will show up in an interferometric measurement. So what we want to compute is ds squared minus dt squared, and then in TT gauge, delta AB plus HAB dxa dxb, which I can rewrite by introducing a parameter lambda, which runs along this direction and takes values from 0 to L. And since at the end I'm going to want to be taking the square root of this thing, I'm going to write it in a way that will make it easier to do so. So I'm going to write this here as 1 plus 1/2 HAB LA LB square d lambda squared. Okay, so what I've done is I've replaced the dxa with LA d lambda, contracted this delta, and then I've Taylor expanded the root and taken the square again. The reason I've done that is that now we see that the thing that is going to make the difference between this guy and this guy is going to be coming from this term here. So the time delay that we're going to get just from going in a single direction along a single arm is 1/2 LA LB, just this term here. And now we have to integrate along lambda HAB, use lambda here to parameterize where we are, so it enters both in the time coordinate and in the spatial coordinate d lambda. Okay, so that's the time delay that the photon picks up due to a gravitational wave when propagating from here to here. Now, what we actually want is not that time delay, but we want the photon to go back, and then we want to compare with the other arm, right? So we need to do the same thing minus return trip. Right, so it will be the exact same expression, just that you've shifted your coordinate origin from here to here, right? So you will have a t0 and an x0 appearing in here, and the LA will be minus LA. And then we have to do the second arm. And then you get some expression, which I'm not going to write down explicitly, but which we can just parameterize as something, so it's a sum over the polarizations, and then it's something that parameterizes all the geometry of the detector. That's what we call the detector response function, this f of k. And then something that has the information on the gravitational wave. So the Fourier coefficient in this case of the gravitational wave, and everything will be proportional, let me put it up front, to the detector arm length. Okay, and the explicit expression for this guy you get by performing this integral. Yes?
So should they be plus return trip and minus second arm?
Yes. Thank you. So sorry, this is confusing notation. This lambda is not this lambda. Sorry, this is, let me call this twiddle. This was the parameter along the propagation direction. This was the polarization. So this is just plus and cross. There's not enough letters. Initially, I was calling the lambda s, but then I had ds squared and ds squared. That wasn't any better. Any other questions?
What is the function f? Is that the sensitivity function?
So f is the response function of the detector. It's not yet the sensitivity, because we haven't talked about noise sources yet. Okay, but it basically encodes, it's a purely geometric function, right? Because you remember what it looked like. I mean, these guys, right, were just a polarization tensor, right, times some coefficient h lambda tilde, right? Basically times the exponential just with the omega kx. So this is a purely geometric thing which just encodes the geometry of the detector.
It should just depend on the angle between k and e hat, right?
It depends, yeah, so exactly. So it depends, it basically depends on the geometry of the detector relative to the direction of your gravitational wave, which is in k. So it basically describes what people call the antenna pattern of the detector, right? It tells you how sensitive am I to gravitational waves from different directions. Here you will find that you are maximally sensitive to gravitational wave coming in or out of the board, where you have zero sensitivity if you're coming at a 40, well, depends on the polarization, right? But either, for example, you can have zero sensitivity to one of the polarizations if you're just coming here at 45 degrees because you're doing the same thing to both arms. Okay. So, and then we have the delta t, right? The delta t basically amounts to a delta phi, a phase difference, right? And then the phase difference is what we read out here at the beam splitter. The reason this works so well is that here we're talking about distance of kilometers. Actually, the effective distance is even more, right? Because actually there's a cavity here and the light bounces back and forth 1,000 times. So the effective distance is more like 1,000 kilometers. But then we're using an optical laser, right? So then we're making a phase difference on the wavelength of an optical laser. And it's this huge hierarchy of scales, which makes this so sensitive and makes it such that you can actually detect if this mirror moves by about the width of a proton, right? We can detect it, right? That is the sensitivity of LIGO.
Isn't it more sensitive than that?
It's a bit more sensitive than that, yes.
Sorry. Yeah, so when we do that integral, you basically put out a factor L. So you're assuming that HAB is a constant when you do that integral.
Can you repeat the question?
So when you do the integral d lambda,
Yeah.
you pull out a factor of L. So
Yeah.
are you assuming that HAB TT is a constant?
No, I mean, HABTT is just the gravitational wave in the TT frame, right? So, I mean, this is the argument, right? So it depends both on time and on position. The L comes from doing the integral from 0 to L, right? And that's the L that then goes up front. Right? It's a matter of convention, right? I could also have said lambda goes from 0 to 1, and then I would have had the L showing up already in this expression. But it makes sense, right? I mean, the further you travel, the more phase difference you can pick up, until, of course, if the gravitational wave makes a full oscillation here, then you lose, right? But LIGO is in a limit where you kind of, this entire during this entire travel time, the gravitational wave makes less than one oscillation, and so the longer you travel, the more phase you pick up. Okay, how does it work in practice? I mean, in practice, you can imagine that you have many things that might wobble your mirror a little bit, right? So a key in doing the analysis is having two detectors, right? Because if you have two detectors, you can look for coincident events that happen in both detectors. If it doesn't happen in both detectors, it wasn't a gravitational wave. Or maybe it was, but it came at a silly angle, right? So better even you have three detectors, then you avoid that problem. The other thing that you can do if you have two detectors, and that will be important for tomorrow for stochastic background, you can cross-correlate between the two detectors. And then you can hope that the noise is not cross-correlated between the two detectors, but your signal will be cross-correlated. Now, that's not entirely true because there are noise components that are correlated across the United States. For example, lightning strokes, right? So lightning that hits at the wrong place impacts the power grid and actually impacts both detectors. So they have to monitor lightning and put vetoes if they think it could have impacted the detectors. So that's just an example to tell you the theory is simple. Doing the experiment is very, very, very difficult, right? And there's decades of expertise in beating down the noise levels to be actually able to make these measurements. And a lot of tricks go into here. So results. What have we seen? With LV, LIGO, Virgo, Cagra, well, I mean, mainly LIGO, to be honest, right? We've seen about 100 black hole mergers. You may remember for the first few, they make big press releases. Then there were no more big press releases, right? That's not because they just stopped detecting the events, right? It's just because you can't do a big press release every other day. But so we're currently so the LIGO observing room 4A has completed early this year, which is months and months and months of data. We haven't really seen the results yet, right? So we're waiting that could come out soonish, right? And again, I mean, we're expecting really, I mean, sensitivity is gone. This is the longest observation run so far. Really expect that they've seen a lot of things. And then observation run 4B is currently ongoing until the end of the year. So again, another long observation run with good sensitivity, where we expect even more data. So this number is only going to go up fast. And then we've seen a few events which were either black hole neutron star or neutron star events. And the future of this is, okay, I mean, LIGO and, I mean, the whole collaboration is still running, right? I mean, LIGO, as I said, is LIGO and Virgo are currently taking data. Cagra is an interferometer in Japan, which is actually, I mean, it has a lot of the technology that is actually planned for the next generation of gravitational wave instruments. So it's using squeezed light, it's using cooling, it's underground. They've been having a lot of trouble to get to the design sensitivity, right? Which just shows you how hard it is to build such an experiment, even if you know in theory how to do it. But they will get there, right? They will get there, and then they will also be contributing. And the more detectors you have, the more it helps to break various degeneracies. These will go up quite a bit. And then the game changer will be the next generation of experiments, right? So the next generation of experiments will be, well, hopefully be, right? None of them is funded yet. The Einstein Telescope in Europe or Cosmic Explorer in the US, which will have significantly better sensitivity because they go far on the ground, where you avoid the seismic noise, or a lot of the seismic noise, which is the main background component in LIGO. Slightly longer arm lengths, cooling, squeezed light, all sorts of clever techniques. And there, the sensitivity is expected to be so good that they can see black holes to a redshift up to star formation rate, which means they'll see all black hole mergers, so stellar origin black hole mergers in the entire observable universe. That's cool. And this is not too far away, right? I mean, people are talking about 2030s for pending funding, right, for having these things online. OK, that's as much I wanted to say on the detectors. Any questions? OK, good. Yeah, you want to hear about BSM, I know. OK, so some highlights. So the first thing you can maybe do, coming back to your question, a test of GR. Actually, you can do many tests of GR, right? I mean, for example, here in GR, you have only these two, the plus and the cross polarization. If you go beyond GR, massive gravity, you have more polarizations. And if you have more detectors, once you have more detectors, you have access to polarization information. So that's one way, for example, to checking if there's more degrees of freedom in GR than just the two that we expect from GR. If there are more degrees of freedom and more propagating gravitational degrees of freedom than the two that we expect from GR. But that's not what I want to talk about. What I want to talk about is a neutron star merger, which carries the name gravitate. So this is how they label the events. So this is just the year, right? So 2017, August 17. That's when they saw the event. And this event was special because it was the merger of two neutron stars. And while for black hole mergers, we don't expect to see an optical counterpart, right? We don't expect to see them in the EM spectrum. For neutron stars, we can see them in the EM spectrum if we're in the light cone that is kind of generated at the merger. Okay, so you have to be lucky, right? Because it's going to the EM radiation is going to be emitted into a very narrow beam into the universe, and you have to find yourself in that beam, otherwise you're not going to see it. And you have to catch it, right? Because the sky is big. So what happened here is that they, LIGO Virgo, saw a gravitational wave event. The masses that they inferred were compatible with neutron star masses, right? So it was fairly light masses. And so they put out an alert for optical telescopes, basically immediately, right? Fast pipeline, saying we saw something. It might be neutron stars. And it's here. Please look. And then people looked, right? And we got super lucky because we saw it, right? I think the first one was Fermi who saw it. They saw basically on the data they had on record, they saw a galaxy suddenly brightening up, right? So they basically caught the merger in the optical. And then because once they saw it, they, of course, could go from ginormous sky localization to actually pinpointing the host galaxy. And pinpointing the host galaxy means you know the redshift. Okay, and then it means once you know where it is, all these optical telescopes, which have tiny field of views, they know exactly where to look. And then they observe that spot, right? And then so there were optical observations ranging from essentially immediately up to days and weeks after the event. And so what you learn, so you have the optical counterpart. Right, and that means, So one, it means you have the redshift. And we'll get to that in a second. But also it means since they were able to catch it immediately, right? So from they got it from gamma ray to radio over a time of basically instantaneously to 10 days. What you can do is you can compare the arrival time of your photons with the arrival time of your gravitational waves. And that tells you something about the speed at which gravitational wave travels. And that tells you something about, gives you an upper bound on any mass of gravity model that you would want to put. Now, there is the one unknown in the game, and the one unknown is that once the thing merges and you kind of emit all your energy, the gravitational waves will just kind of immediately go out and travel. The photons may get stuck a bit, right? Because they kind of, there's medium around that, right? And there may be a delay time in the emission of the photon because the photons have to go through some sort of medium. And you don't know exactly what that is, which is why the bound is not perfectly symmetric in both directions. But what you learn is that the difference that we can have between the speed of travel speed of the gravitational wave with respect to the speed of light has a lower bound of -3 times 10 to minus 15 and an upper bound of 7 times 10 to the minus 16. And this is a super stringent bound, right? This killed a whole bunch of kind of beyond GR theories with a single observation. So this is a strong constraint on massive gravity. Questions? Yeah.
Which events are more frequent? The black hole merging, or?
Yeah. So the questions are which events are more emergent? You mean between these two, or between this one and this one?
Yeah.
So I mean, the black holes are much more frequent, right? Because we've seen 100 of them, right? And we've seen very few of them. Now, between these two, we don't actually know exactly. So A, there's very few. So there's only been a single neutron star merger where we've seen the optical counterpart. That means we know for sure who's two neutron stars. We have a bunch of events where we have two relatively light objects merging, but we're not entirely sure if this is neutron star black hole or neutron star, right? It's kind of compatible with both. So we don't really know. So but then it could still be neutron star, and we were just not within the cone, or we didn't see it. Or it could be black hole. We don't know. But we have basically one confirmed neutron star event and a handful of events that fall in this category.
How, you might have just answered that question, but still just to clarify, how do they differentiate between the three events, if at all?
Right, so the question is how do you differentiate between these different types of events? So the primary distinction is the mass. Okay, so there's an upper bound on the mass of neutron stars, which is like few solar masses or something like that. No, even less than that, right? But like order one-ish solar masses, right? 2, good. 2 is order 1. So if you see something which is much heavier, it's clearly a black hole, right? Well, clearly a black hole, right? I mean, among the known astrophysical objects, it is a black hole, right? At least it's not a neutron star. Then once you have a light object, right? Okay, there's also a lower bound on the stellar origin black holes, right? The Chandrasekhar mass. So anything below 1.4 solar masses is not a stellar origin black hole. So the main criterion is the mass. But now you can do a bit better. So A, if you see an optical counterpart, right, it was a neutron star. B, if you manage to observe the merger phase, you can observe these deformability parameters. And then in principle, for black holes, they don't deform, right? So these lambda is 1. And for neutron stars, you would get some deformability. Now, it turns out that measuring this merger phase is very difficult because for these light objects, that's just kind of at the edge of the sensitivity curve of LIGO. Right? So at the moment, we don't really have good bounds on the deformability for any of these events. And definitely no clear measurement that it's not a black hole. But we will get there, right? With a bit more sensitivity, we will be able to use that criterion to really determine if it's a black hole or not.
I was also wondering, like, why is it that there is really no optical counterpart for black hole merger, in the sense that you might have some accretion disk that somehow can emit, I don't know, you would see a brightening of two accretion disks.
Right. So the question is, why is there no counterpart for black hole mergers? If you have supermassive black holes, right, they have these big accretion disks, and then you do have optical counterparts. So when you talk about LISA, right, we can have optical counterparts. Now these stellar origin black holes, they are small black holes, right, and they tend to not have a big accretion disk, right? So I think I think there was not complete clarity about this question until we started observing the things, and we saw that there's no optical counterpart. This is astrophysics, right? You make a kind of something, right? And you make an observation, and then you reform your model. Yes?
Have there been experiments which are coming up or studies which correlate the optical spectrum with the gravitational wave spectrum?
Right, so the question is if there's correlations of the optical with the gravitational wave spectrum. Yes, okay, so this is a concrete example, right, where you really use both the optical and the gravitational waves. Now, something that is going to be coming up is that now that we get this many events, right, you can kind of starting basically making probability heat maps of where you saw the gravitational waves, and you can correlate that with galaxy catalogs. Actually, I'll talk about that in a second, because by doing that, you can kind of do a probabilistic assignment of a host galaxy without actually seeing the optical counterpart. But I'll get back to that in a few minutes. OK, so let's do another one, which is a test of lambda CDM. And more precisely of the Hubble constant. And I'm going to, again, use that same event, right? So again, with that neutron star merger. So how does it work, right? So I told you that with gravitational waves, we measure the luminosity distance, right? So dl is 1 plus z d. Optical, if we identify, or EM, I should say, right? It doesn't have to be optical. If we identify the host galaxy, right, which we succeeded in this case, we can do kind of spectroscopic analysis of the host galaxy, we know the redshift, right? So we get Z from the host galaxy. And now you can plug this into Hubble's law. Right, so redshift is Hubble constant times luminosity distance. And you can get a measurement of the Hubble parameter. So from this one single event, what they saw is the following. OK, so this is just the probability as a function of Hubble in the usual units of, well, we don't even need units. I think all that you care about is that Planck is here, right? And the superbuzz or distance ladder, right? So let's say shoes, for example, is here, right? And now we can do a measurement from this neutron star event. What we find for the posterior, if we do this analysis, is some thing that is peaked perfectly in between and pretty broad, OK? So it's a very, very diplomatic measurement, right? But this is a single measurement, OK? If we see more of these events, right, you gain statistics, and you will kind of shrink the error bars, right? And then you will have a measurement which is completely independent of all the distant ladder stories, and is a late time measurement of the Hubble parameter. I mean, the philosophy is exactly the same as in the distance ladders, just that you don't need a distance ladder, you just do it in one go. Now, the problem is, OK, we saw this one event, but we've only seen one, right? So it's a bit hard. We don't know exactly how many more to expect, how fast. So we kind of don't know how fast are these error bars going to shrink. So in the meantime, people have come up with a different idea, which is what I was referring to earlier, and that is even if you don't see the optical counterpart, if you have enough measurements, right, and so for each, let's even take the black hole mergers, right? So I have a black hole merger, I have some pretty crappy sky localization, right? Though the more detectors I have, the better it gets, but it's way not good enough to identify the host galaxy, right? It's really a blob in the sky. But if I have many, many measurements, and I cross-correlate that with galaxy catalogs, I can assign essentially a probability, a weight, to finding this event with a certain host galaxy. And then I can play the same game, right? So at a kind of a statistical level, if I have enough events, I can play this game. So while this thing is called, if you want, a bright standard siren. So standard siren, like standard candle for supernova, and bright because we saw the optical counterpart. There's the alternative is what is called the dark standard sirens. Which is this statistical approach simply based on many, many measurements. And that's to answer your question. I mean, that's exactly an example where you would really cross-correlate a map that you get from gravitational waves with a map that you get from EM observations with the galaxy catalog, and you try to learn something about cosmology. Okay, and then the last test that I want to mention for LIGO is formation. Or more directly, black hole formation. So what you can do if you have 100 events is that you can start making a distribution about distribution of masses that you've observed, right? And as I said, in leading order, you only have access to the chirp mass, not to the individual masses. But then as you identify close enough your merger phase, you do have access to the two individual masses with some error bars. So what you can do then is you can make a plot, basically number of events you've observed with a given mass for the black hole. And you find from the data that's public so far, so up to the third observation run with LIGO, is that it starts at about 6 solar masses, maybe. Then there's a peak. And there's another peak around 35 solar masses. And then it kind of goes down to about 8. Well, let's put, say, 70 is here. And it goes to about 80. Now, if you're an astrophysicist, this is very disturbing at first glance, because everything is power laws in astrophysics. This is not a power law, right? So I think they would have been happy with whatever power law you found, right? But this is not a power law, right? So the fact that this is not a power law means it has to be a combination of power laws, right? So there's a combination of processes that we can describe with power laws, right? So what's going on here? Okay, so the first question is what's going on here, right? So we expect that there should be no black holes below the Chandrasekhar limit, right? So 1.4 solar masses. If we saw a black hole below that limit, it would be a primordial black hole, right? There's really no other way to get it. Haven't seen that yet, or at least if we have, we were not able to distinguish it from a neutron star, which is why we need that resolution in the merger. But 1.4 solar masses is not 6 solar masses, right? So this is what is called the lower mass gap. And there are some ideas of why there is a mass gap here, which is something to do with how the core collapse supernova works, and maybe, well, I mean, I think it's just kind of an idea that maybe the core collapse supernova has some dynamics that should be the dominant supernova mechanism in this mass range, and maybe there's some dynamics that somehow doesn't allow them to collapse if they're very light. However, now more recently, there have been a few events which are kind of maybe in that mass range. So for people doing supernova, this is very exciting because there's stuff to understand here. Okay, so then you have, these guys are all core collapse supernova. Then around 35 solar masses, the idea is that you go from core collapse supernova to kind of instability. Well, okay, so well, I'm not a supernova expert. Let me be more vague. So the idea is that around these 30, but also I think people don't really know. But the idea is a bit that different supernova mechanisms kind of, this may be a transition point between two different mechanisms. And this might explain a bit what's going around here at 35 solar masses. Yes? This is the mass of the individual black holes. It's both, right? I mean, it's just all the black holes that we've measured. And then here there's also, this is maybe the most troubling part, because the way people understand supernovas at high mass ranges is that you get these so-called pair instability supernovas, but they shouldn't leave a black hole remnant. At least not a black hole remnant of this mass, because there's a whole bunch of stuff that just gets kind of blown away into space and it doesn't collapse back into a black hole. So basically the statement was that above 50, maybe above 70, you shouldn't be generating black holes anymore, right? 70 was really the kind of hard upper limit for what you should see in black holes. Now, we've seen events above that, right? Actually, this is M1. In each event, we see 3 black holes, and they all go in here. So one explanation for these heavy guys is that, okay, maybe they're formed by multiple mergers from light guys, right? That's a possibility. Or maybe there's accretion, but it seems a bit hard to get enough accretion to really get up into this very high mass range. So this is, for people doing supernovas and star formation, this is very exciting, right? Because it means there's maybe something we don't, because also this peak, right? I mean, this peak could be due either to something we're doing with the supernovas, or it could be something to do with stellar environments and some distribution of stars, right? Maybe there's more stars at this mass range because something in star formation that we don't fully understand yet, right? So this is more astrophysics. And I would say the error bands on astrophysics models are so large that I personally wouldn't invest in a BSM model trying to explain this. So of course people have kind of postulated that maybe these are primordial black holes up here, right? Because it's hard to get the supernova to do it. I think that's a bit premature, but just to tell you that there have been kind of a lot of results, which at the moment I think are more interesting for astrophysicists. But you know, once the dust settles a bit, that's definitely a place, once we understand this better, that there's a lot of information that we previously didn't have.
Do we have any correlation with the redshift or the distance?
Okay, so the question is any correlation with redshift and distance. Yeah, so in the catalog paper where this plot is from, they do have a plot with correlation with distance. I don't think there was a strong correlation, but I'm not sure. But also LIGO doesn't measure out to very high redshifts yet, right? I think we will. So this is another proposal, for example, how you would potentially distinguish stellar origin from primordial black holes, right? Even if they're in the same mass range, is that as you go to higher redshift, you expect the stellar origin to follow the star formation history and the primordial to just be flat or be whatever they are. So we don't have that sensitivity yet, but with the Einstein telescope or Kobe Explorer, we will get there, right? Because then we will measure out to high redshift or LISA. Yeah.
Like you mentioned, some of these black holes have accretion disks. So usually with that, you get these like radio jets that you can observe. Is there some counterpart?
Right. So the question was about accretion disks. So for these stellar origin black holes, I don't think they have sizable accretion disks. What I mentioned is that they accrete, right? So it means they can gain a bit of mass over time. but we haven't seen a single optical counterpart that we can associate with a black hole merger. Yeah.
I think you mentioned that couldn't we explain like that entail with like subsequent mergers of multiple black holes, or there's less probability to find like all the black holes together close to each other?
Exactly. It's so the question is, could we explain this high end tail with multiple mergers? And potentially yes, right? I mean, actually, in fact, some of these guys are actually there because we've literally observed their merger, right? But it's still, yeah, people still find it a bit challenging to. I mean, I guess it's a question of probabilistics and merger rates and whatnot, right? So I think it's still a bit challenging to explain. Because also the thing is, if you see so many up here, right, it means that correspondingly it's basically, maybe if you understand this peak, right, that would a bit tell you why this is going up so far, right? Because it might be the mergers of these guys that are pushing you here. I mean, there could also still be selection bias effects, right, and cosmic variance effects, right? I mean, 100 is a big number, but it's not a crazy high number. Though they made this curve already after the second observation run, and the structure is exactly the same. The only things that have changed is that now it's not clear if this is actually a gap or if there's actually some events here.
Maybe a follow-up question. What is the percentage of mass that get lost after the merging?
Ah, very good. So the question was, what is the percentage of mass that gets lost after the merging? A few percent. So it's about 4% or so. That gets lost into gravitational waves, which is a lot, right? This is like if you have a 30 solar mass black hole merger, it's a solar mass of gravitational wave radiation that is blown out into the universe. Yeah.
Like this number 4%, it's only for black hole merger, or does it depend, I guess, for neutron merger that would probably be different?
No, it doesn't actually. So the question was if the number 4% depends on if it's a black hole or a neutron star. No, it actually doesn't, because you can get nearly, because the fact if it's a black hole or a neutron star, this 4% you get in the Newtonian approximation, right? Because what you do is you do the Newtonian approximation of energy loss, and you extrapolate until what is called the ISCO, the innermost circular orbits, when these guys touch. So yes, kind of the neutron star will touch when it's slightly further apart than a black hole, right? So in that sense, that number will change, right? But I can't give you a number, but in a straightforward way, right? You need to do the same calculation, but you put a different radius as an endpoint. Which is, this is one of the approximations that works despite that it shouldn't, right? It kind of gives you the correct number despite you're actually not in the range where it's justified to use it. Okay, so then in the last few minutes, actually we'll fit here. Let me talk about LISA, right? So that's space telescope scheduled to launch in the 2030s, early 2030s. This is approved. This is an ESA mission with NASA partnership. It's funded, right? So as long as the rocket doesn't blow up in the launch, right? I mean, this thing is going to fly. Yeah, no comment. So what is the idea? The idea is you have 3 satellites, right? And you exchange laser links between all the satellites, right? So fundamentally, again, it's an interferometer. The difference is it's in space. It has arm lengths of 2.5 million kilometers. That means if you convert that to frequency, right, it will have a lower frequency in the kilohertz range. And the satellites will be flying on an orbit around the sun, trailing the Earth, right? And the 3 orbits will be slightly tilted, one against the other, so that you always form an equilateral triangle. And then as you go around the Earth, so the Earth is here, due to the tilted orbits, kind of the instrument rotates once around itself. But it's basically free falling on these orbits, and it stays at leading order equilateral. Now, there's challenges, right? I mean, already the fact that you want to, it's up there, right? There's no way we can get at it anymore. It's far away, right? I mean, this is a big distance, right? This is much further than the distance to the moon. And you have to shoot a laser satellite and hit the satellite, right? Right, in order to do this measurement, right? So technologically, right, this is something for, right? But that people are pretty confident that they can do, right? And there have been test missions. There's been the Pathfinder mission, which didn't test this part of the mission, but of how well can you, because you have these test masses inside a lot attach the test mass or something, right? It's a bad idea in a rocket launch to have something loosely flying around. Up there, you have to release the test masses because the test masses are going to be really freely floating, and the satellite is just kind of protecting them from kind of micro meteorites and stuff like that, and dust and whatnot, right? But basically, the test masses are supposed to be freely floating inside of the body of the satellite. So if you release your test masses and you give them some minimal velocity in the process, you're screwed, right? So the part of this Pathfinder mission was to do one satellite, bring the test masses up, and show that you can keep the test masses at free falling, measure the distance between the two test masses with the required accuracy to do this experiment. And it actually did significantly better than mission requirement. So it really showed that that part of the mission is under control. So what can you do? So science, I mean, you can do many, many things with LISA, right? And the key mission objectives are astrophysics, because that we know is there, and that's kind of guaranteed deliverables. But for us, I think it's more exciting, how can we do for fundamental physics, right? So what you can do is, again, an H0 measurement. As we discussed before, you can use bright standard sirens, right? Because now you have decretion disks. Or you can use dark standard sirens, right? As we discussed before. But now you're doing it with supermassive black holes. So you're going out to very high redshift, right? So you can do a measurement of the Hubble parameter as a redshift dependent quantity out to, I don't know, redshift, I don't know, but a few, right? I mean, more than just a very local universe. You can, and another exciting object are what is called the extreme mass ratio inspirals. So these are objects where you have a heavy black hole, a supermassive black hole in the middle, and a light black hole, which is in a bound orbit. And then if you look at what this orbit looks like, it will do something like this, right? So what that means is that this light guy is really mapping out the metric around the heavy guy, right? So if the metric of the heavy guy is not perfectly Schwarzschild, if there's anything there, right, this is basically as a test mass to really scan the entire environment about the heavy guy. And there can be many, 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 many orbits, right? Many, 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 many orbits before this guy kind of finally merges. So that's a test of black holes and the near field environment of black holes, so strong gravity, which we have no other way to test. And then, of course, LISA has such good sensitivity that we hope we will be able to see stochastic gravitational wave backgrounds, right? So there's some that we know that we'll see. We will see astrophysical ones from unresolved white dwarf mergers. But there's a big hope, right? That, I mean, LISA, as we saw, is the right frequency range to probe the electric phase transition. So one of the things that we'll talk about next lecture is how kind of to use stochastic backgrounds to look for actually cosmological sources. And then we'll really be talking about particle physics and know more about gravity. And just to mention that with LISA, but also in Telescope and the COBE Explorer, there's a huge data analysis challenge coming up, right? Because so far, LIGO, despite all the events that we've seen, LIGO is a signal sparse detector, right? So most of the time they measure noise, and they can optimize, and they can twiddle, and they can make it perfect, right? And every once in a while they have a signal, and then they have, you have a signal every other day, right? I mean, so there's really no problem with data storage or analyzing the data, latency, all that. I mean, the only latency issue was to do the quick alerts for the optical follow-up, right? But otherwise, a priori, you have time. With LISA, we're going to have, a priori, hundreds at the same time, right? Same with the Einstein telescope. You see black hole mergers in the universe. That's a lot, right? So the signal will be, the detector will be full of signal. We will not have any downtime because we cannot shield gravity, right? So it becomes a completely different data analysis question. It's more like thinking about pileup in the LHC, right? You have lots of parameters, you have lots of data, you're no longer noise dominated, and you have to disentangle a lot of possible signals to do parameter reconstruction, right? So it's very much more like an LHC problem than it is a LIGO problem. And that's, I mention that because I think that's something which is at the moment a very much underdeveloped field, and where kind of I think people with particle physics expertise could have a huge impact in thinking about more clever data analysis techniques than what we're using at the moment. And that's a good time to stop.
Great, perfect timing. So let me announce briefly